In 6.2, we are going to get into how exactly does a nerve transport information from one place to another. We're going to learn about how nerves are actually involved in electrical signaling, but there are also some chemical components to it as well. So the first thing is that neurons have something very similar to muscles that we talked about. We talked about muscles having certain behavioral properties, and neurons actually have two specific behavioral properties. One of them is irritability, which basically says that neurons have the ability, like muscles, to respond to a stimulus. But neurons also can do something else called conductivity, which is another behavioral property, which is basically they are able to take the stimulus that they receive or stimuli they receive, and they are able to convert it to a nerve impulse. And so we're going to see how this comes into play and how this actually happens. So the first thing is that a nerve impulse, what is it? So a nerve impulse is a small electrical charge that actually is able to pass between neurons and transport or transmit information. And they're able to transmit information through something called action potentials. And we're going to talk exactly about what these action potentials are, but just remember, action potentials are these electrical impulses that travel down nerves or neurons and communicate between other neurons or between a neuron and a muscle. So this is kind of an overview of an action potential. You might look at this graph and remember it from the last section, we're going to talk about the breakdown of it. So the first phase that we're going to talk about is called the resting phase. Then your neuron's going to go through something called depolarization. Then they're going to go through something called the rising phase. Then they're going to fall. They're going to go through a phase called the falling phase of the action potential. And then they have the undershoot. So this image kind of color codes all of them based off of this graph. And then we're going to break it apart right now. So the first part of the action potential is called the resting phase. In the resting phase, this is also known as the inactive phase. So if you want to write that next to resting phase, aka inactive phase, you are going to have potassium ions that are going to be located in the cell. And then you're going to have a lot of sodium ions that are going to be located outside of the neuron. Because of this, location of potassium and sodium, you are going to have the cell be more negative on the inside than it is going to be on the outside. So you can kind of look in the diagram and you can see how the inside of the cell, which is the cytosol part, is going to be a lot more negative than the outside of the cell where you have the extracellular fluid, which is going to be more positive. Now, the change and the difference in these charges with positive more on the outside, negative more on the inside, this causes the cell membrane of the neuron to be polarized. So anytime you hear polar, that means there's always a difference in charge. And so because you have a difference in charge on either side of the membrane, you have polarized membrane. So this is kind of another image that shows you the inside of the cell has more potassium, outside has more sodium, and then you see the difference in the charges. Outside is more positive, inside is more negative. Then we move on to the next part, which is called depolarization. So in depolarization, you have a stimuli that's going to come in and activate the neuron. Things like super bright light, if your parents are trying to wake you up and they open up the shade and you're like, why are you doing that? That can trigger it. Something really sweet or sour or bitter on your tongue. And even the movement of neurotransmitters between the neurons. All of these can cause a stimuli, which is going to activate a neuron. Now, the stimuli that you get has to exceed beyond a specific critical voltage level in order for it to actually trigger the neuron to be activated. And so when you do have a stimulus, though, that triggers a neuron to be activated, you're going to have a couple things happen. One is that the sodium-gated channels, which are located in the membrane, they're going to open for a brief moment, and when they open, all the sodium, or not all of them, but a lot of sodium ions from the outside of the cell are going to rush into the cell. When this happens, you are going to create an electrical charge inside of the membrane. Therefore, the inside of the membrane is now going to be more positive than negative. And the neuron membrane is now going to be called depolarized. So now you have kind of an you kind of have a similar charge between the outside and the inside. It's no longer going to be more negative on the inside. It's going to be more positive because of the rush of the sodium ions that come in. So you can see in this image, on the right, you can see the sodium ion channels that open up, and the sodium is coming into the cell. Therefore, the cell on the inside that was usually negative is now turning more positive. Continuing with depolarization, in order for depolarization, when depolarization happens, you're going to have this kind of occur throughout the entire neuron. So you're going to have a bunch of these sodium channels continue to open along the entire neuron. So it's going to create like a wave-like effect of depolarization to occur. And then this wave is also known as an action potential. So this electrical wave of depolarization that moves across the entire neuron is known as an impulse, or known as your action potential. Your action potential causes something called an all or none phenomena, which basically means that you have the same amount of electrical impulse throughout the entire neuron, and it's going to go from one end all the way to the other. So it's not going to stop in the middle. You're not going to have different levels of electrical impulse or nerve impulse. They're all going to be the same, and they're all going to go from start to finish. So you can kind of see in this side on the right that you are slowly starting to make your way down. Obviously, it's not actually occurring slowly. This is actually occurring very fast, but you are having this movement of charge going down the neuron itself. So this is the graph that we kind of saw earlier. You see that where you have depolarization occurring here, which is the opening and voltage gated sodium channels. And then the next part is going to be repolarization. So let's talk about repolarization. In repolarization, you are going to have, once the action potential has been discharged, right? You have depolarization happening, you have an action potential being sent off, your membrane is going to be more permeable now. And because it's more permeable, it's going to allow your potassium ions that were once inside of the cell to leave the cell. When this happens, when your potassium ions go out and leave the cell, your membrane of the cell is now going to start to get restored back to its original polarized state. And this whole process is called repolarization. Makes sense, right? You're trying to bring it back to its original polarized state, also known as its resting state. So anytime you have resting state, think of polarized, the change in charges between the inside and the outside of the membrane. Anytime you have an action potential being created, it's being depolarized. And then anytime you see repolarization, that is when the membrane is trying to get back to its original state. Again, you see that in this image here, the potassium ions channels open up, so potassium is able to leave the cell, creating back this repolarization or resting state, or bringing the neuron back to normal. Now, this is really important, the return back to normal, because if your cell membrane is not able to be repolarized, it cannot respond to another stimulus until it has done so. And this is called the refractory period. So the refractory period is basically the time between you have an action potential or nerve impulse being released, and then the return of the neuron back to its polarized state, or return to repolarization. And this is known as the fatigued stage because it's so exhausted that it can't handle another nerve impulse until it has returned back to its resting stage. So you see that, you see in the last part, the return back to its resting stage, kind of what happens during the refractory period. We're going to skip through these. So in what stage of the action potential are the sodium gates open and the potassium gates closed? So sodium gates are going to be open during the depolarization phase. And then the potassium gates are still closed. And then the potassium gates will be open during the repolarization phase. In what stage of the action potential are the sodium gates open and the potassium gates closed? This kind of gets a little bit too in-depth, so we're going to just skip this question. Why is the inside of the neurolema negative and the outside positive at the start of an action potential? Remember, it needs to be polarized in order for the action potential to occur, but the inside is negative because there's a low amount of positive ions, obviously, inside of the neuron, therefore it's more negative inside. And then when the sodium gates open in the depolarization phase, there's a heavy movement of sodium ions into the cell and a large amount of sodium channels in the membrane, which causes this change. Therefore, you have depolarization occurring. How does the inside of the cell return to a negative charge after an action potential? When you have the exchange of sodium potassium, because of the pump that they have, which basically allows the leaving and coming in of these ions, you have 3 specifically sodium ions that come out of the cell and 2 potassium that goes into the cell. Because remember, when we start off in polarization, you have more sodium outside and more potassium inside. You are going to return back to the original state of the neuron. Okay, so now we're going to talk about impulse transmission. 2 things that determine the speed of an impulse transmission, aka an action potential, is how thick the axon is, so the diameter, as well as if the axon has a myelin sheath or not. Remember, myelin sheath is an insulated, electrical unit, kind of like an electrical insulator, and so the presence of myelin sheath is very good because it allows for fast transmission. So when we talk about fast transmission, like I said, you have a faster transmission of action potentials when you have a myelin sheath. So when your neuron is unmyelinated, you are not going to have a fast transmission of electrons. So saltatory conduction is basically when you have the impulses jumping from one myelin sheath to another, because remember, they're not continuously connected. And you have the ability for depolarization to occur at the nodes of Ranvier. So depolarization only occurs at the nodes of Ranvier. So you can kind of see in the image where the purple is showing right here. The purple is showing the myelinated sheath, and you don't have very close contact between the charges. So you're not having depolarization occur there. They're only occurring at the nodes of Ranvier where the charges are close enough for depolarization to occur. Diameter, so conduction is faster, obviously, in non-myelinated neurons with larger diameters because you have more of a current and ion flow. So the larger the axon, the more number of ions you have, and the more current is going to be conducted. This is kind of like if you have a larger pipe, you have more water that's being able to be moved, then and you have more water that actually is being traveled through the pipe than if it was smaller. Body temperature also affects the amount of, impulses that's traveling, because if you have a warm body temperature, you have an increase in ion diffusion. Therefore, you're able to kind of be more sensitive. Cool causes a decrease in ion diffusion. So if you hold an ice cube over, say you got a scratch and it's like throbbing, you put an ice cube on it, you're going to notice that it kind of goes numb after a while because you're slowing down the ion diffusion and the ability for the action potential to travel Therefore, you're not going to feel it as much. Okay, so some cells are able to communicate with direct transfer or direct contact through something called gap junction. So cardiac muscles, for example, they have intercalated discs and they are able to communicate with each other in this fashion. But there are some that have to use electrical impulses in order to communicate between neurons, especially through the synaptic cleft or the synapse. So what happens at an electrical chemical event? First of all, the main communication that neurons have with each other and with muscles are going to happen through the synapse. Synapse is that gap that you have between the end of an axon terminal with another neuron, with the starting of another neuron or a muscle fiber. Action potentials are electrical signals, are going to rely on electrical signals or electrical impulses. But when you have a reaction occurring at the synapse, they're going to rely on chemical because you're releasing neurotransmitters. So when you have the movement of neurons or communication between neurons, they're called electrical chemical because electro from the action potential and chemical from the release of neurotransmitters at the synapse. So what exactly happens? The first thing that's happened is you have an action potential that's released, travels down the neuron, and ends up in the axon terminal. What you see in the image, the yellow part, that's the little bulbous end, that's the axon terminal. The axon terminal then will depolarize, right? So depolarization is when you have the change in charge on the inside turning more positive than negative. When this happens, the depolarization is going to cause calcium ions to come into the terminal through calcium ion channels. When the calcium ions come into the axon terminal, this is going to trigger these vesicles that are in the axon terminal holding a bunch of neurotransmitters. Those vesicles are going to fuse with the membrane at the bottom of the axon terminal, which you can see here. So you can see that the vesicles are these little like bubble looking things. When the calcium ions come in, they're going to come to the bottom of the axon terminal, fuse with the membrane of the axon terminal, and release what looks like almost like turquoise little little substances, which are the neurotransmitters. And the neurotransmitters will now be released into the synaptic cleft or the synapse. Once they're released, those neurotransmitters will find receptors on either another neuron or a muscle fiber. In this case, it's a muscle fiber. And they will cause a reaction there or continue with the stimulus and communication. Now, there are two types of neurotransmitters. There's ones that can be excitatory or inhibitory. The excitatory neurotransmitters are your acetylcholine. So these are what is going to cause an action in your muscle fibers to make you move. There's also called inhibitory neurotransmitters, which are called like your endorphins. They are the ones that block nerve cells from discharging pain signals. So a lot of times when you're like working out and you're not feeling so good, and then you go for a nice workout or a nice run, or like even emotionally, like if you're like having a rough day and you go for a nice run, a lot of people come back and they're like, oh, I feel awesome. That's because you have released a bunch of endorphins, which now are blocking those pain signals or in your body, and they actually make you feel a lot better. The important thing when you have neurotransmitters being released into the synaptic cleft is that there has to be a way for you to remove them after they have done their job. If you just leave them there, you can cause overstimulation, and that can be really bad for your body. So there has to be some kind of method for a reuptake of these neurotransmitters. Usually what happens is you have some kind of enzyme that correlates with the specific type of neurotransmitter that will take up the excess neurotransmitters. So like acetylcholine that's been released, they actually get deactivated by an enzyme called acetylcholine esterase, which is specific for acetylcholine so that it doesn't cause overstimulation. Lastly, we have to talk about reflexes. Obviously, we all know reflexes because we all have reflexes, hopefully. So reflexes are just rapid involuntary responses to stimuli, something that you're like, if you ever do something, like someone throws a ball at you, you haven't really like realized there's a ball coming at you and you catch it anyway, that's your sudden reflex, right? A lot of times you are more prone to have a proper reflex when you are more used to like that sport or something. Or you can have a reflex if you touch something hot, automatically you take your hand away. You're not going to just keep it there until you're like, oh, this is really uncomfortable. Maybe I should take my hand off. It's an automatic thing. Or like someone pretends to like throw something at you and you blink, or like you kind of jerk away and you're like, oh, that's a reflex. So, when you have a transmission of impulses, they're going to travel through something called a reflex arc, which basically is connected to your peripheral nervous system and your central nervous system. And so sometimes your reflexes need your brain to say something. So say like you're encountering something for the first time, you don't really know what it is, your brain will send a signal saying, hey, this is dangerous or whatever, we need to get away from this. But sometimes you don't even need your brain to send the signal. Your spinal cord can actually send the signal out automatically. So like a lot of times if you have like a ball coming at you, for example, someone throws something at you, your hand will move before your brain even registers there's a ball coming at you. And that's something that your CNS or your spinal, cord can actually send out signals to. Kind of same thing like when you're driving and you're like, how do I like remember? I don't even remember how I got to my house, but you're like so used to driving to your house that it kind of just happens naturally. So there's two types of reflexes. There's somatic and autonomic. Somatic has to refer to your skeletal muscles, so SS. So this is like your rapid reflex. So these are quick movements that you have. Example, touching a hot stove, immediately you remove your hand. Autonomic reflexes, like it says in the name, it's something that's automatically being done in your body without you having to make a conscious control over it. So this is when you have like you're eating food, you don't have to consciously say to your stomach and your intestines, hey, digest the burger that I just ate, digest the fries that I just ate. Also like sweating, if you're like really panicking or you're playing a sport, your way your body cools you down is through automatic reflexes. So you're sweating, increase in blood pressure, which is what BP is or whatever, to compensate for what your body is going through. So this is it for 6.2. Make sure you take your notes, make sure you copy this, and then we will continue with 6.3 in the next video.